Hello students, welcome to the series of lectures on digital speech processing. So in this video I am going to explain about the classroom discussion topic, that is time domain methods for the speech processing, zero crossing rate. So in the previous video we have already analyzed what is the short time energy, okay, and how we are going to be analyzing the speech signal by taking the speech segment on a short period of time. Okay, now let us look into the zero crossing rate. This is also one of the most important time domain method for the speech processing. So let's get started. So on completion of this lecture, you will be able to illustrate the short time processing of the speech signal. So in the context of the discrete time signals, a zero crossing is said to occur if successive samples of the different algebraic signs and the rate at which zero crossings occur, which is a simple measure of the frequency content of a signal. So here what we are analyzing is that, so how much speech signal that you are going to be speaking on a time frame. So the rate at which the zero crossings occur is a simple measure of the frequency content of the signal. So in that signal, what is the content of the frequency signal? That means after converting from the time domain into the frequency domain, we'll be having a spectrum. So there is a spectrum contains the lot of frequency components in it. Okay. So zero crossing rate, which is a measure of number of times in a given time interval per frame that the amplitude of the speech signal passes through a value of 0. So you can also imagine a sinusoidal curve. Okay, so as an example I'm telling, if you take the sinusoidal curve, okay, from the zero axis, so when you take the several cycles, for instance, take the 5 cycles for instance, so on this zero axis, so how many number of times it crosses the zero line. Okay, so zero crossing rate, which is a measure of number of times in a given time interval per frame that the amplitude of the speech signal passes through a value of 0. So that is going to be passes through a value of 0. When you imagine the waveform of a sinusoidal, you can easily understand. And this is very important. Speech signals or broadband signals and interpretation of the average zero crossing rate is therefore much less precise. Okay, so because zero crossing rate is especially useful for the narrowband signals, not for the broadband signals. As I clearly mentioned in this slide, the first point is the speech signals or the broadband signals, so that zero crossing rate is a less precise. Okay, so however, the rough estimates of the spectral properties that can be obtained using a representation based on the short time average zero crossing rate. Okay, now this is a definition. Actually, from the definition we can easily look into this of the zero crossing rate is that Zn is equals to, so summation m is equals to minus infinite to infinite, the signum function of the speech. So what you need to identify here, x of m is the speech signal, okay, and you are going to be taking the signum function, okay, and minus signum of x of m minus 1. This is the first difference, of the sigmoid, and we are taking the difference of the sigmoid function or the signum function. Okay, and that is multiplied with the window properties. Okay, the window coefficient, that is w of n minus m. Okay, and you can also clearly visualize. So this is the block representation, how we have written as per the definition, we have written this mathematical expression. The same thing we can also see the pictorial representation like this. So x of n, that is the speech signal, we are giving to the signum function. So this is the representation of the signum function, and at the output of the first block, which is the signum of x of n. So this we clearly mentioned here, that is the first part, and after that we'll be having the first difference of that, that is x of m minus 1 is the first difference, and we are taking the magnitude of these two, signum of x of m and then signum of x of m minus 1, we are taking the magnitude, and we are processing that speech signal to the any kind of the filter. So here if I take the low pass filter, we'll be having the low pass filter coefficient. So one thing we need to remember is that we need to design a filter in such a way that we have to focus on the speech content and what is the coefficient of the speech content. In that way we need to analyze the speech content of the coefficients, and also we need to put the filter coefficients in that way. Okay, so it has to suitable that. So the low pass filter coefficient that can be multiplied with the speech signal, and you'll be having the at the output of the low pass filter is a zero crossing rate. Okay, and from the definition of the signum function, signum of x of m is equals to 1. So when x of m is greater than or equal to 0, and which is minus 1 when x of m is less than 0. This is the, by definition, we can easily understand from the signum function. Okay, and this is the window coefficient w of m is equals to 1 upon 2n, and the limits also by clearly mentioned from 0 to n minus 1. The m varies from 0 to n minus 1. Okay, so if m equal to 0, obviously w of m equal to infinite, and if m equal to n minus 1, and something that we'll be getting from this. Okay, so overall what we need to understand is that, so this is the way how we are going to be representing the speech function. First we need to apply the signum function, and we are going to be taking the first difference, and we are taking the mod, that's a magnitude. Okay, so when you analyze the pictorial representation of the speech signal in the time domain, we are taking the magnitude of that. The peaks we are going to be taking the magnitude, and that will be multiplied with the window coefficient, so that you will be getting the zero crossing rate. That we are calling as the short time average zero crossing rate. The name itself indicates the average, nothing but we are taking the magnitude. Okay, so that we are going to be evaluating the peaks of the each and every speech content of the signal. Okay. Thank you, students. Thank you for watching this video.